Great, thank you, Ben. Thanks for having me here. Yeah, Ben told me that this was informal, so I got excited and put together a whole bunch of stuff that I normally don't get to talk about. So we'll see how that goes. So I'm excited to present it. And apologies for the yellow. It's my university color. It's just such a weird color. You never see it, but there you go. So I'll start by acknowledging my group. So we're called the White Lab, which was the least offensive variation on white we could come up with. The white group didn't sound good. So there you go. So this is my group. I asked them to put together a funny picture, because I got sick of all the mask pictures. And it took a long time for us to do this. You put a camera in front of someone and you say, do a funny picture. And there's a lot of discussions. This is what we came up with. I hope you like it. And throughout this talk, I'm going to talk a lot about little sort of side projects that we've done or that I've done personally. And we collect them down here at the bottom here. So I don't know, it's kind of like an Easter egg. So if you want to look back at any of the things I talk about today that are non-science, I try to collect the interesting projects down here, these little buttons to click. And, they're meant to be a little bit fun. There's no labels. You can experiment to see what they are. Oh yeah, and we're a research group too. So here's our funding sources. I should acknowledge them. All the great scientists that work with me in my research group, and our collaborators, and we publish papers, believe it or not. So in my talk today, a lot of what we do involves deep learning. And I don't want this to be like a tutorial in deep learning, but deep learning is the exciting new area in AI that drives a lot of the advances. So if you hear excitement about machine learning and about AI, most of the advances lately have come from deep learning. And deep learning is actually really sort of a simple idea. And the idea is that if you have some function, f of x, where you have an input of x, which is typically a vector, or it can be higher order, like a tensor, and then y is a scalar, and you want to basically learn what the function is, what is f of x. So if anybody's done linear regression, this should sound familiar, right? But in linear regression, you have to assume it's a line. Maybe you've done some nonlinear regression. That is, you maybe choose a few functional forms you might believe that f of x could be. But in deep learning, people discovered that with a little bit of work, you can represent sort of any function as this simple equation here. So this is kind of the classic dense neural network equation. So that is, we have x being our input, w being some trainable matrix, multiply w by x, add a constant, put it through nonlinearity. And it turns out there's some math that you can show you can approximate any function with this. So deep learning is kind of like linear regression, except for we can approximate any function. And any function means like even the Schrodinger equation, which underpins quantum mechanics. So it's a simple idea, but it's been incredible how powerful and how many things you can accomplish by being able to approximate functions given data. What is possible with this? So I'll just show you guys some examples. So, I know when you see the equation, f of x, it can really narrow your thinking, but here is one where x, like the input is a sentence, robot doing chemistry, and the output y is like an image, right? So this is the image that's being generated. It's incredible because on the one hand, deep learning is definitely like a mathematical technique, and it's definitely, a bunch of linear algebra and tensor operations, but it is able to capture things that, we think are so, I don't know, far away from mathematics like art. And I think it's a really exciting time to be in the field of deep learning. Here's another one. So I didn't, explain what changes here, but this one was like a robot doing chemistry, and I said it's a pencil drawing. And this one I said is a 3D render. And so it's kind of incredible that this model is able to accomplish these things. Now I'm brushing over a whole bunch if you're a deep learning practitioner. Obviously, I've lied a little bit because this is actually an adversarial network that is guided by a model which can connect images to text. But basically the principle is the same though. So, right, deep learning is building these equations, and when we stack these together, we call it a neural network. A neural network is probably one of the greatest tragedies in nomenclature. There's nothing neural about it. I think some people still cling to the idea that there's some sort of fundamental connection between neurons in your head and neurons in neural networks, but really neural networks should be not thought of as some sort of giant connected graph that mimics the brain. Neural networks are just stacks of linear algebra with some nonlinear functions sprinkled in between them. And, in a lot of ways, people began with the idea that neural networks should just be dense layers, like just that equation I showed you. But there's a really important idea, what is there to be done in deep learning, then you might ask? Well, this is the idea of inductive biases. And that is explicit choices we make in constructing neural networks that reflect data generation or solution space. That's a very computer sciencey word to say, like the physics, right? So when we construct these neural networks, we need to think carefully about the physics of the underlying system. So I'm a chemical engineer, so I'm going to give you examples in chemistry, but this is sort of where a lot of the work is in deep learning these days, is that how do you make these function approximations, these neural networks, obey the laws of physics, the symmetries, or capture this underlying reality or physics problem we want to keep. So in chemistry, we can think about molecules in a few ways. I've shown here 2 ways to view a molecule. One is what's called a molecular graph, where we view a molecule with a Lewis dot structure, where we have bonds, valencies, satisfied octets. On the right-hand side, I have the same molecule, but drawn using point clouds. So we think about it as these are where atoms are. The atoms are certain elements. So like blue is nitrogen, gray is carbon. I think they're equivalent, right? They kind of are capturing different things though. But it turns out that when you use that representation, you have sort of chosen inductive bias. And when you write down a molecular graph, one of these chemical structures, you're saying that you believe there's atom permutation equivariance. It's a very fancy word, and let me break it down here. So the way we represent a molecular graph is with 2 things. We write down what atoms are in our molecular graph, and then we write down how they're connected. So atom permutation equivariance just says that if I were to write down the atoms in this molecule here, I've written them down, only the first 10 atoms, and then I'm representing them with a matrix. And so each column indicates what the element is. And then I use a 1 to indicate the element being carbon here, and a 0 for oxygen and nitrogen, because it's not oxygen or nitrogen. So atom 0 is a carbon, right? And then not an oxygen, not a nitrogen. And then what I'm showing you here is the output of a function. So this is the output of the neural network. So it should be, say, 0.3. So I could be predicting, say, partial charge, or I could be predicting whatever, the magnetic susceptibility. But what permutation equivariance says that if I were to swap the order, like if I were to now change it so that atom 3 is the first thing in this matrix, and then atom 0 is the fourth thing in this matrix, my output function should also swap. And this sounds so simple, right? Like it's like, yes, if you swap the order of the atoms, then the output of the neural network should also swap. But it turns out a dense neural network won't capture this. But this is really critical for chemistry, because there is no one true way to write down a list of atoms, because we know that atom ordering is arbitrary. Just like we know if you measure on an NMR spectra that the hydrogens that are equivalent will all show up in the same peak. Now, if we go over to the point cloud representation, looking at atoms, we also have things like translation equivariance and rotation equivariance. So here I'm showing you a little trajectory of a polymer. And then the red is the output for my neural network. And you'll see that as my polymer translates, I need my output of my neural network to also translate. And as my polymer rotates, I need the output to also rotate. And it's crazy to think that these things, which should be so obvious, they were actually really hard to make neural networks learn. And so what people would do is they would sort of just try to teach the neural network by giving it lots of data to capture these things. But with some work, deep learning has been able to do things like predict energies 6 orders of magnitude faster than DFT that are correct. We can do things like relax an organic molecule on a metal surface without doing any quantum mechanics. We can find the relaxed structure. Or there's something like AlphaFold. We can fold proteins now from the DNA information. So basically the sequence of the protein, we can now fold them just with deep learning. You can fold a protein in 2 minutes on your phone. It's incredible. And a lot of it has been simple ideas, like the AlphaFold thing was rotation and translation equivariance. That was really what helped the protein folding model work and at a level that's accurate enough to be useful. So I think it's interesting because sometimes we spend time in deep learning thinking about very simple ideas like symmetries and equivariances. But just because of the power of deep learning being able to learn functions, we don't have to think about the functions. We just need to think about properties of the functions, which I think is a very interesting way of doing science. So if you're doing deep learning, we have this problem or opportunity, depending on how you want to view it, that we can view molecules in different representations. And those different representations have different equivariances implied, right? Like a molecular graph, although we pretend like molecular graphs can capture stereochemistry, even this picture I'm showing you has, it implies an enantiomer because it has that dashed line there. Even though there's no, there is a stereo center right there. Yeah, perfect. Yeah, so that chirality is not actually captured in a molecular graph. It only is captured in a point cloud. We try to give hints to it when we draw them, but it's not really in a representation of a graph. Or if we go down on the left, the smile string of a molecule, which is a way of writing down a molecule. It's like naming it, for example. It gives it a unique sequence of letters that maps back to the molecule. If you try to do deep learning with that representation, you lose permutation equivariance because there's a certain order to how you write down a molecule in a smile string. I'll come back to this in a little while, but each of these representations has trade-offs, but really at the end of the day, if you can do smiles and do deep learning with the smiles of a molecule, it is so fast you can write it in JavaScript and have it run on a web browser. And I'll show you some projects that I've done that are, I think, incredible what you can do now and just running on a website. You can do deep learning in chemistry. And then point clouds, these are things which are very difficult. It requires bespoke kernels, sophisticated packages. It's a very evolving area. So it can do powerful things, but I think you only want to touch point clouds if you need translation and rotation equivariance, like if you're trying to predict the dipole moment of a molecule, for example. Okay, so that is my introduction about deep learning, about the ideas or what is sort of the science that's being done there in chemistry. I'm going to start talking about things that are not off the rails, but I'm going to kind of get into some of the non-science stuff that we do with deep learning or that we do with programming and computational chemistry. I know there's a little bit of a stream delay, but I'm just going to take a break here and drink some tea. And Ben, if there's any questions, I'm happy to take them now, or if you have any questions.
Absolutely. Can you hear me all right?
Mm-hmm.
Okay. So yeah, I actually have a couple of questions. You made this may be something that you kind of get into more as you talk about specific projects, but I'll go ahead and ask it now. What are kind of the pitfalls of deep learning? Like, what are the things that you have to watch out for when you're setting something like this up? So that, because certainly it's possible to introduce your own bias into the results and things like that. So how, maybe in a very general sense, what are the good practices that people doing this kind of work should follow to make sure that you're not sort of tipping the scales basically towards what you think the outcome should be?
Sure, yeah. So if you take a deep learning course, probably 50% of the course is going to be about how to regularize or reduce overfitting. That is, because these things are so good at fitting data, you can have a problem where you've sort of overfit to your small training data size, or you've overfit to noise in your training data. That's actually an endemic problem, I think, in computational chemistry and machine learning work, is that people overfit to training data. So I think, the zeroth order question is, how do you be sure that what you're looking at is accurate performance, or that you've really not overfit to your data or overfit in your construction, is to split your data in 3 ways. And so this is something I won't talk about too much in my projects. It's just kind of a standard method. But what you do is, if you have 100 data points, this is obviously, don't do deep learning if you have 100 data points. But yeah, if you have 100 data points, you would basically make, say, 60 of them be for training, 20 of them would be for validation. And validation is a strange concept, I think, to most people. But the idea is that when I'm training my model, I have to make a lot of decisions about the architecture. Like I can choose how many layers, how deep are they, whether to have these different equivariances. And those decisions should be made on your validation data set, because you don't want to overfit, right? So you won't know if translation equivariance is important until you look at the validation data, that is the data that wasn't used to train the network. However, at the end of the day, you will have been tuning your model to that validation data. So at the end of your project, I said use 60 and 20, there's 20 data points left over. Then you'll do at the very end of your project an analysis on those 20 data points to see how good your model is. And that's what you'll report, is that if somebody uses your model on new data, they should expect that performance. And that kind of, I don't know, people call it like hygiene or something, or cleanliness or tidiness, is that you want to separate your data really cleanly so that you can capture correctly how good your models are. And that's, I think, a lot of the work that goes into making sure that your deep learning work is actually capturing what you think it's doing, is by being really careful about separating your data.
That makes a lot of sense. Again, sort of kind of high level for somebody that's not familiar with the area, what are the limitations of the deep learning systems, I guess? Or is it, so you talked about like smiles versus the 2D drawing versus 3D drawing.
Yeah.
Is it just the amount of information you're trying to process, or are there other factors you have to consider?
Sure. So let me break that up into two things. So one thing is like, what are the weaknesses of deep learning? Or so sure. Deep learning is it's a data driven method, right? So you need data. There are some really exciting work, and we've written papers on this, where you can get down to like 5 data points or 1 data point. But at the end of the day, it's something where you need to be able to capture your problem setting into a data point. And that's not true all the time, right? Like, I don't know, for example, let's say you're running a refinery, a chemical engineering refinery. Mm-hmm. You're not going to go down there and try 10 different settings of running the refinery and see what happens, sure. And then write down the data, right? And then you might say like, oh, well, we could just change the parameters a little bit and see what happens. And it's like, well, I mean, first of all, it's probably illegal and unsafe, but even if you could do that, there's this correlation. Like each time you do those measurements, it's going to be highly correlated with what was going on, 10 minutes ago or 5 minutes ago. So there's no concept really, I think, in online control of like, cleanly separated data points. Sure. There's ways to get around that, but I think that at the end of the day, these are methods where you need to have this idea of being able to capture data point and characterize it. And then as far as the representations go, like this is something we think about a lot, is that you want to use the representation that is as simple as possible, but can capture what you're trying to model. And I'm going to have a specific example that'll make this more concrete, but just to give you one example, like let's say you want to predict, the partial charge on an atom. Mm-hmm. If you use Smiles, you're going to have a bad time because Smiles doesn't explicitly model every atom, right? Like Smiles makes the hydrogens implicit. Mm-hmm. So you wouldn't be able to get all the atoms. So then you could use a molecular graph, and that would capture, so you could do the partial charges. And let's say you want to do something like, I want to predict, I don't know, the dipole moment. Well, a molecular graph wouldn't have 3-dimensional coordinates. Yep. So you could make a very sophisticated deep learning method that will predict the 3D coordinates and then also give you dipole moment, but it might make more sense to just represent things in 3D coordinates ahead of time. So very simple. I think these are very simple ideas, but that's sort of what drives the choice of representation.
Okay, that's a good explanation, because like I said, that makes a lot more sense in terms of how everything needs to be set up to do it properly. Yeah. So is, again, general question, is the goal with deep learning to have a system, in an ideal case, to have a system that's very flexible? So to give us kind of specific example, I work in electrolysis, and one of the things that we try and do is sort of similar to what you just talked about with the online parameter changes. Like, we take our electrolyzer, we collect some data, and then we want to be able to not have to just shotgun everything and do, like you said, 10, 15 experiments, measure the results. Even though we can collect clean data that's not affected by previous results, it's still a lot of work. It's time intensive, labor intensive, resource intensive. And it's a lot better if we can predict ahead of time what we expect to happen, and then maybe do like 1 or 2 test cases and see if our model is correct.
Yeah.
But that's still going to be a very focused model. It's going to be for our particular system. Maybe somebody else should be able to build the same system and see the same results based on what we see, but it's only for that particular system. So is it reasonable to say that, or again, sort of a goal of deep learning to be able to take a more generalized picture and apply it in a lot of different ways, or is deep learning going to give you a really strong system for a particular set of or for a particular problem, let's say?
Yeah, that's a really good question. So what you're describing, I think, would be best approached with a method called Bayesian optimization.
Mm-hmm.
And Bayesian optimization is a kernel, but it doesn't have to be, but typically is the kernel method. Mm-hmm. So that is, it will take a system exactly like what you're describing, like some electrochemical system, and you want to just basically try different parameters and see what happens, and you want to explore intelligently. That's a classic Bayesian optimization problem. So that is not deep learning, but it's from machine learning. Mm-hmm. And it gets into something that is challenging right now, is that in deep learning, uncertainty prediction, so having error bars at all your points, is kind of weak in deep learning, or it's difficult to do. But there are other methods like Gaussian process regression, which is what's used in Bayesian optimization. That are quite good at that, but they work well for a small amount of data. Anyway, but let's move on, because I think all these questions are going to make more sense once we see some real projects here.
Sounds good. Take it away.
So the first project I want to talk about is something I made called Chem Hover. And so the idea of Chem Hover was that I made it's a plugin you can put on your Firefox browser, and what it does is it basically identifies smile strings and then draws them as chemical structures. And so I started this project, and what I thought would be really cool is that if we could just ingest the entire web page and look for any smile strings and then draw them as chemical structures. And so I wrote a machine learning model, a deep learning model, that could look through HTML to find smile strings. And this is a great example of deep learning, is that finding a smile string is something that maybe you could construct a computer program that could identify a smile string, but it would be a very brittle process, right? Because you might say, oh, if there's lots of C's, or if there's equal signs, if there's parentheses, right? You can imagine trying to do something, but it would be not very good, or it would be very difficult. So, but I was able to train a neural network to do this, and it could just take in an entire HTML and then find all the smile strings. And so I wrote a plugin, and I was really excited about it. And then I went to some websites, and it just crashed, because it turns out that there's a whole lot of HTML on a typical web page, and running it through a neural network doesn't work well. So I had to sort of scale back my idea. And so what it does is, whenever you select something, it looks at the HTML around it and identifies where a smile string is. Then it throws up 2 emojis, because why not? And then draws a molecular structure. What I think is exciting about this project is that this thing, from start to finish, took, I don't know, maybe 10 hours, probably less. Most of the time was spent figuring out how the hell to write a browser plugin. But it's incredible to me how mature it is that I can show, this is everything I'm talking about is open source on my GitHub page. You can basically go and see the source code for training this machine learning model to discriminate smile strings in HTML. And it's such a simple idea. I didn't even write a paper or anything about it, but like maybe 10 years ago, this would have been, actually, this was a real problem like 10 years ago. It's called chemical entity recognition. And people were writing dozens of papers. There were PhD theses on how do you identify a molecular structure in text. And I could solve it now in just a couple hours. It's crazy how fast this moves. So there was one project that I did. And surprisingly, this is the least popular project I think I've ever done on Twitter. Not many people were interested in it, but that's life. So another one about applying deep learning is something called Emoji Math. So I don't know if you guys saw, like on social media, people were showing all these emoji equations, and I decided to make a real Emoji Math. So this is a legitimate tool you can go to and plug in arbitrary equations of emojis, and it will solve them. So the first one is like a crown minus the female plus the male, and it shows you the best matches. So the top match is a queen. Minus a male, plus a male. Here's one. Here is the if you wanted to know, here's the dot product of a man and a woman. It's about 0.33. So there you go. And if you take the sign of the castle emoji, you get the pagoda emoji. And I thought that was a very fascinating equation. So I think I have it over here. So here it is. It's in a Google Colab. You can do it right now. So like here is a smiley face plus a cat makes a cat smiley face. Makes a lot of sense. We could do a smiley face times a cat face, which gives you a coal factory. I have no idea what that could possibly mean, but there you go. Maybe a smiley face minus a cat. Oh, a closed eyes smiley face. Wow, fascinating. So just to tell you how this is made is that I didn't do the science part of this. This is from a paper by Ben Eisner from a couple of years ago. But what they did is they basically used a machine learning technique. It's very related to deep learning, but not technically not deep learning, to learn a vector for every emoji. So what happens is that every single emoji is actually a vector, and then you can do arbitrary vector operations on them. And then at the end, we find what vector is closest to it. And you might be wondering, how the heck do you embed an emoji in a vector space? And it's by looking at similar emojis. So it's like if you see two words occurring in the same context, then those words are probably synonyms. And you can capture that by building a vector space that finds these things. And so this was a classic paper in machine learning called Word2Vec, and then basically these people did Emoji2Vec, and then I actually turned it into something you can use so that you can do Emoji Math. And this is also a command line tool that you can use. So if you ever want to install more useless command line interface tools, you can install Emoji Math so you can do quick emoji calculations from the terminal. So then, I don't know why, but I thought, about emojis a lot after this. And then I made this picture. I said, I think we're all sick of molecular structures with letters. Why don't we make all the molecular structures with emojis? And I thought about like what should be the oxygen, what should be like the hydrogen and the carbon. And it was popular on Twitter. And I thought, and after I made this tweet, I have a problem with overthinking things. I just kept thinking about, could you actually do this? And so I think like maybe 2 days later, I actually made Emoji Chem. So Emoji Chem is a drawer that you can open up in Colab if you want to do it. Basically, you plug in smiles string, and then it will draw the molecule using emojis. Now, I have to say that I spent a lot of time learning how to overwrite SVG. So the way this works is that RDKit draws the molecule, and then I edit the SVG using some Python to replace the letters with emojis. I couldn't get the darn emojis to lay out as cleanly as I wanted. I mean, so it has been a constant thing that I think about at night is how do I fix Emoji Chem? But luckily I've held myself back to focus on, writing proposals and research papers. But I think this is really kind of a interesting project for me. And it also kind of got me into this cycle of like, I wrote this in I think maybe 1 or 2 days of like being able to write a package, getting it up on a Google Colab, writing a README. And I think this kind of epitomizes open science, although I don't know if I characterize this as science, but just basically, writing everything quickly, transparently, and distributably and executable as quickly as possible. So let's see. So that was Emoji Chem. And then, so then after that, I had learned a lot about composing SVGs. And then one of the problems I came across is that in matplotlib, which is the plotting library of Python, it's not actually possible to put SVGs together. So then I wrote like a little library that basically allows you to put arbitrary SVG images. So here's like a way to annotate a plot in matplotlib. And now I'm putting an SVG image of a skunk. And then I'm also annotating this point up here with the plot itself. So it's like a nested thing. I'm annotating with the plot of itself. I thought that was kind of cool. But anyway, I think what was interesting for me is that I got it down to like an exact science where I could go from the code to getting it packaged into an installable Python package to have sort of GitHub actions. So GitHub is where I store all the source code that can basically, every time I push the source code, it launches a new version of the package, it tests it. and then putting it all into like a Google Colab so that people can play with the code immediately. And it's been, I maybe started this in August, and I've made, I don't know, maybe 10 Python packages in a very short amount of time. And it's kind of exciting how mature the tools are that allow you to execute any kind of idea. And I'll just show the one that I made, I think, last weekend. So this one is called TurnViz. So I'll just show you the bot. So it's like a little bot, and what you do is you just tweet at it, and you say TurnViz render, and then you give the smiles string. And if you want to know how to find like a smile string, you can just Google a molecule, and you can get the smiles off Wikipedia or something. And then TurnViz, the bot, will then render the structure. And it even looks up the name. This one doesn't have a name. So, and this is, again, something that we just sort of put together in a short amount of time. I tend to do these things when I have deadlines. I had a proposal that was due, so rather than work on the proposal, I wrote this bot. But luckily, the proposal deadline was pushed back a week because of COVID. Yeah, I don't know. I don't know what the point of all these projects are. I just made them all, and I thought I'd share them. Happy to take any questions on them. And yeah, so I'll take a little break here, and then I'll get back into some science.
Sounds good. So yeah, I'll jump in. We've got a couple of questions. First of all, I didn't realize it was you that had made TurnViz. I saw it around Twitter, which that's fantastic. I thoroughly enjoyed it.
Thanks.
So your first question here: with open source science, do meaningful contributors to repos get a chance to collaborate on papers? And this person's asking, what are some good places to see if we can pitch in?
Yeah, so there have been a couple good papers that basically turned the GitHub contributor list into co-authors on the manuscript. Okay. One maybe example would be the Plumed Nest paper. This is a paper put out by the Plume developers in Nature Methods, maybe like 2 years ago. I think the paper, it's gone like bonanza. I think it was like 350 citations in 12 months. And there's like maybe 35 authors, and it was everybody who made like a meaningful contribution to that package. And I mean, I think everybody had academic affiliation on that project. But there's another project I'm on, and the paper's not out yet, but I'm on another project where basically the people who were the maintainers of this repo reached out to people who have been contributing to this ecosystem and said, hey, you guys want to help write a paper? They organize it in Discord, and there's people on that paper who are non-academic affiliated. So I think it's possible to get on papers and to contribute to science if you're not a professor, if you're not a PhD student. Actually, there's one person on the paper I know who's like a PhD student from another group, but their PI had nothing to do with it. They were just doing it in their free time. So I think it is possible. It's difficult, though. Like, one of the problems is that a lot of the things I do, it's really hard to distribute ownership. Like, for example, TurnViz. Like, I don't know how I could have someone help on this project. I mean, it's possible. Like, there are open problems on it, but maybe small problems. I mean, if anybody wants to help me, like, I love PRs. I review PRs. I'm all about it. I'd love to work with anybody on this stuff. And a lot of the stuff I do, like when I approach these projects, these are definitely not science, pure science. Like TurnViz, I use existing algorithms. I hack my way. Like, for example, coming up with the names, I just query somebody else's research project that turns smiles into names. Like, I didn't try to invent anything there. So some of the projects I think are just trying to have fun. Like, this is just, I thought it looked cool. I don't think there's going to be scientific outcome. Like, I don't know, what else did I have on here? Skunk? Yeah. No, definitely not writing a paper about skunk. Emoji Chem? Maybe someday.
Maybe, yeah.
Yeah. I think if I've been drinking, I might submit that to a research paper.
Get the emojis into the 3D, configuration that you need.
Oh yeah, there we go.
Then we can talk. So
Yeah. Emoji Math, maybe someday. Chem Hover. This is like, Chem Hover is something that's so funny to me, because like if I wrote this like 5 years ago, this would be a very exciting paper. But now I don't even know if it's worth writing up. But anyway, I don't know. Like, I think there's always opportunities to connect. I mean, I'm not very good about advertising things, but I do have a textbook called Deep Learning for Molecules and Materials, and that's been a really great model. Is that the textbook is on GitHub. It's an executable textbook, so you can load any chapter from the textbook and immediately execute the code on it. And I've had, maybe 10 PRs, maybe 60 issues opened on the textbook. And it's been like a collaboratively written textbook for the community of computational chemists for deep learning and molecules and materials. So I think that's another area if you're more software inclined, or you're not maybe in this space, but you want to contribute. Like that textbook is a great place to contribute. If you don't want to just write code.
Very cool. That's awesome. Let's see. So I got somebody asking about convolutional neural networks. Says they're very good at image analysis. Is it possible to modify one to include an additional input layer that would pass electrochemical data to improve the predictive power of that model?
Yeah, so convolutional neural networks have been sort of generalized. So yeah, you're right. Originally, or not originally, but they were developed for images, and they're very good at that. But there are things like convolutions over graphs, convolutions over point clouds. People have sort of expanded the architecture to cover a lot of different areas. So for your specific questions about like including electrochemical data with images, if there's a lot of work, I think they might call it like multimodal data that is taking in data that describes the same system, but the data is different modes, like an image and maybe text, or in your example, like an image and maybe like a plot or some vector. Excuse me. So yeah, that's definitely an area that goes in. One of the things about deep learning is maybe a pro and a con is that a lot of the work is driven empirically. Like, it's hard to know if an idea is good or bad until you try it out on data. And some ideas work on some data and some ideas work on other data. It's a very empirical field, although the way we try to organize things is with these equivariances. The way I try to organize things is with these equivariances and these inductive biases. But a question like that, you just got to try it.
Okay. Do you think these modeling methods can be used to make AR tools for learning in undergrad courses?
Oh, have you been reading my papers? Yes. I have written 2 papers on using projects like this on AR and VR and undergraduate education.
Okay.
2 papers, 3 papers, 3 papers. Yes. So definitely, yes. I've written a couple papers. I don't have anything on it today, but yes, absolutely.
Okay. Awesome. And I think the last one we have right now, so science is already very siloed, even with nice, transparent mathematical formulas. As we start modeling the world with deep learning parameters, do you think the problem of interdisciplinary science will get harder?
No, I think it's going to get a lot easier. And I don't know if it's a culture or if it's something fundamental about deep learning, but when a paper comes out in deep learning, people are using the method like hours after the paper comes out. Like AlphaFold came out in August, and like people have had grants funded. There are hundreds of papers written with AlphaFold. I'm working. God, I'm like really bad. I shouldn't say this. I don't know what I can say. I'm working with patients. Like I'm not working, but I'm working with people who are working with patients on using AlphaFold on real medical problems. So I got to say, deep learning is a field where like in 4 months, this thing is like completely penetrated all these fields. So I think it's the opposite. Deep learning is very good at making things immediately useful and crossing disciplines quickly.
That's awesome. That's a really good thing. I think science is better when there's a lot of collaboration happening.
Yeah, definitely.
That's fantastic. All right. I think that's all the questions we've got for right now. Somebody did ask about getting the links to some of those papers. So maybe after this we can. I'll
sure.
get some of those links from you, and we can share them around.
Yeah.
Good deal.
Okay, so I think one of the themes of my research over the last, by the way, everything I'm talking about here is from 2021, I guess. So one of the themes over the last year has been that text is really powerful. So I think we kind of saw it with ChemHubber, but I want to talk about one particular problem. So this is a website I mocked up. So in deep learning for chemistry, there was a problem that was like, whenever people had a new solution, it was published in Nature Chemistry, or I think that was probably the highest we got was Nature Chemistry. I think there was a Nature Methods paper too, but it was a really exciting problem. And that is, how do you get deep learning models to dream up new molecules? And like, this is something which was a problem that was really difficult. And nowadays, there's been so many interesting breakthroughs in representing molecules and also these deep learning methods that I have made a website in JavaScript where you just go to this website and you just type on the keyboard and it draws new molecules that are reasonable, I think. So I just sit here and bang on this. And I made this because my son, he's kind of falling behind in his organic chemistry. He's not a very good organic chemist right now. And one of his favorite activities is to basically bang on the keyboard. He's 2, by the way. And so I thought that this would be a great way for him to learn a little bit more about organic chemistry and also do his favorite thing is smashing on the keyboard. And so he actually is like, hey, Dad, can we make molecules? And so we go down here and we smash on the keyboard and we make these molecules. Let's just I have a button here to make a big one. Let's see what happens here. Oh, it's not that big. Come on. Maybe something bigger. There we go. That's quite small. Anyway, so this is a project that is something that I just made up. I don't know. This one maybe took 2 days. And it's incredible to me that I can get this running in JavaScript, like a deep neural network and string representations. And this is something which was incredibly difficult, like maybe 4 years ago. Anyway, you guys can check it out. It's called Molecular Dream. I don't know if Googling Molecular Dream brings it up, but it's on one of those little emoji icons on my website. Okay, so that was all about cool stuff you can do with deep learning or maybe just computational chemistry. And now I'm going to talk a little bit about some real science. So this is work, this first project is done by Ziyu Yang and Mikishri Chakraborty. And this is the paper and the code. And I think this is a great sort of story about how we can do something with deep learning that was previously very difficult. When we look at protein structure, what we want to do with protein structure is we want to find the ensemble of conformations. So things like alpha fold, or like if you look at a crystal structure of protein, those are for proteins which have one definite fold. But most proteins, not most, but I would say maybe a third of proteins in the body have disorder to them. So that is just like how we know from Boltzmann distribution, the thermodynamics, that a protein is going to occupy as many states as it possibly can at room temperature. So one of the ways we can measure that is with something called NMR. NMR measures chemical shifts. And a lot of the work that has been done in inferring protein structure is that we look at the chemical shifts and find all the conformations consistent with those chemical shifts. And this is usually done with something like molecular dynamics or Monte Carlo. But at the end of the day, what we need to be able to do is to propose a protein structure and then see what its chemical shifts are. And then we can invert that to find out what is the protein structure from the chemical shifts. So this is kind of like a forward-backwards model problem. But the trick is that to do this correctly, you need to make F be differentiable with respect to the positions. So R is the positions, and then delta is the chemical shifts. So right now, there are some very good methods that are not differentiable, and there are some very bad methods that are differentiable. And what we wanted to do was see if we could use deep learning to solve this problem. It's a great problem because there's data, it's a well-defined function, we know the equivariances. So going back to what I described, we know that chemical shift is a per atom quantity. So each atom has a chemical shift. We can't measure the chemical shifts for all atoms. For example, nitrogen is not typically measured with an NMR machine, or it's difficult. And we know the chemical shift should be position dependent, right? We want to connect the chemical shifts to the structure of the protein. And by the way, if any of you are chemists, you might be thinking like that when you think of NMR, you think about determining the chemical bonds, like what is this compound identity. It turns out with very large macromolecules, the chemical shifts will move up and down field based on the conformation of the molecule. So that's what we're thinking about here. It's not the chemical bonding. We know what the chemical bonds are. We're trying to think about the conformations of it. And chemical shifts should be something that are descriptors. So this is maybe a little bit more sophisticated of an idea, but we wanted to make a model that would work with proteins, small molecules, RNA, DNA across the space. There have been some good models developed that are very specific for the amino acids which make up proteins. We wanted something general. And so based on these sort of constraints, the right neural network architecture would be a graph neural network with relative distances as the edges in the graph. So just thinking about like a molecular graph, instead of a molecular graph where the bonds are like the electronic bonds, the bonds here are the distance between atoms. So here's what it looks like. So here's a protein, and I'm showing you in the light blue, these are now the bonds that we have. These are not bonds as far as like covalent bonds. These are just basically the distance to all of its nearby atoms. So we just use 16 nearest atoms. I'm not going to spend too much time on what a graph neural network is. I think it's a very cool idea, but I've written a book about it. So if you go to my website and go to the deep learning book, you can read all about it. Yeah, here's the citation for it. There's a little animation. I mean, I guess I'll just try to give you a little bit of intuition, but the way a graph neural network works is that it basically sends, this is, by the way, this is one kind of graph neural network. This is a graph convolutional neural network. There are many kinds of graph neural networks, but this one basically sends messages to atoms, and it sort of accumulates information about what it's being bonded with. So the first layer of a graph convolutional network basically replaces this oxygen with the idea of an oxygen bonded to a hydrogen and a carbon. And then the next layer, this oxygen is replaced with a vector that says, you know, you're not just bonded to a hydrogen and a carbon, you're bonded to a hydrogen that's terminal, and you're bonded to a carbon with 3 hydrogens on it. And it's sort of like a way of, you can think about as typing atoms, or like, you know, thinking from atom to functional group to maybe motifs, or whatever we call bigger things. But I'm not going to talk about it too much. So there's a little bit of work to be done here. So the graph neural network allows us to basically capture this graph that I've constructed. And remember, the graph is not the molecular graph. The graph is, I built the graph by just connecting all atoms with information about how close they are. We have to do a little bit of other work here. Is we need to think about like what elements can have a chemical shift. How do we go from element to a vector, and then how do we go from a vector to a chemical shift? So this is just maybe, if you're a deep learning practitioner, some details about how it all fits together. But anyway, we just basically built a neural network that follows those inductive biases. Then we took about 2,000 proteins, and then we took some small molecules just to see if we could do small molecules. This turns into 5 million chemical shifts. The reason why is that proteins have, you know, thousands of atoms, so that's how you get 5 million from 2,000. This is just some details about the network details. And then again, like I said, we split our data up into 20,000 was withheld for testing. And this is just some training information. So I'll just tell you then, so the results. So the first thing to think about is what does the perfect model look like? So R here is correlation. RMSD is root mean squared deviation. So we want a correlation of 1 and an RMSD of 0. So what I'm showing you here at the top is called label variance, which basically means people have measured chemical shifts in proteins multiple times. Like 2 groups will measure the same protein chemical shift. So this is capturing how correlated groups or repeated measurements are. So if you look at a protein twice, you'll have a correlation of 0.97 or so. So that's kind of a difference from maybe what is often done in computational chemistry. This is real data, so there's noise, right? So if somebody repeats the measurement, it doesn't come out the same. So then just showing you our model, it gets about a 0.78 correlation coefficient. So it's pretty far away from perfect, right? Then we compare some other methods. This is a method which is not differentiable, but very accurate. And this is the method which is differentiable, but inaccurate. So we managed to get very close to the best method, but keep that differentiability so that we can use it for the application of inferring protein ensembles. I won't get into the other ones, but just basically we did things like shrink the model, add weighting, do different things with it. And then one of the things we like to do is see what was important for the model to learn. So here I'm showing you the performance on a subset. So it's 0.993 for the subset of atoms. And I'm showing you if I remove the distance information. So now it doesn't know how far away it is from the atoms, just knows which ones are nearby. We get pretty good correlation still. And then here I've removed out the nearby neighbors and only look at covalent bonds. It loses some information. And then this is that reference again, as good as well as you could do. So you can see sort of what is important for the graph neural network. And then, like I said, one of the goals was to make it so that it could work on organic molecules. So here is this correlation 0.87 on organic molecules. So this is now something which can predict chemical shift, which, by the way, if anybody wants to know, like, you can also predict chemical shift with density functional theory. That is quantum chemistry, but it's a very awful and very slow method. So this is basically the best you can do right now for organic molecules. And then sort of the thing we were thinking about a lot for this is what's called a salt bridge. So salt bridge is an important interaction in protein structure. And it's captured in NMR. NMR sees this in experiments, but all the models out there for looking at for predicting NMR chemical shifts, they don't capture this effect. So we're excited to see that our model can actually capture, as a salt bridge is formed, the change in chemical shift. And this is just some information about secondary structure. We capture secondary structure effects as well. So like I said, we try to do open science. So you just do pip install NMR GNN, and then this one line of code here will basically evaluate the chemical shifts. This one's set up for if you have a molecular dynamics trajectory. So to look at a whole bunch of frames from your MD trajectory. I told my student to make it fun, so she put some emojis in it. And then you get out a CSV file with the chemical shifts. You could just look at a single protein structure as well. And like I said, this works on organic molecules and proteins. So that is sort of, I think, a typical deep learning project. So there is a real problem in the field, that is, how do you predict chemical shifts for proteins? And then we solved it. And what's cool about deep learning is we solved it so hard that you can now do this task with one line of Python code, which was previously non-differentiable, very difficult, and it's a portable environment as well. I think we even have a Google Colab, so you can do it from your phone or from a web browser as well. So I want to get to the other side. So I said interpretability. So I want to talk a little bit about how do you actually learn things with deep learning. So I hopefully I've convinced you that you can be accurate with deep learning, but at the end of the day, we're scientists, so we need to actually learn science and test hypotheses, not just be accurate. Although I guess I'm an engineer, so I can get away with this most of the time. So let's talk a little bit about how do we explain outcomes from deep learning models. So this paper is a preprint a few months ago. I think this is one of my most exciting papers. We wrote this paper in I think from start to finish in 10 days. What the student here, Aditi is her name. She's an undergraduate student. She just had this brilliant idea. She came up with this concept, and we just my student Gimi and I were like, wow, that's an incredible idea. We have to do this immediately. So Aditi happened to be on summer break, and so Gimi and I crunched and we got it all put together. We made a really cool paper. So let's start. So in deep learning, there's this idea that we build these giant complicated neural networks. There's no hope of looking at the neural network weights or anything to get any kind of interpretability. It's just not intrinsic of neural networks. You can't look at them and reason about them. So what we typically do in deep learning is that we try to explain one prediction at a time. So don't try to explain the whole function, just try to explain its reasoning for one specific prediction. So just a little bit of nomenclature here. So we'll say something like the justification is why you should trust the neural network. So that would be its accuracy or its test error. The interpretability is what I just described before, is that how much can you learn from just staring at the model. So interpretability, like I said, in deep learning is kind of an oxymoron. You're not going to get interpretable by just looking at the model. So an explanation is a way to sort of bridge that gap and give information for people that helps you understand a specific prediction. So there are lots of papers on this in deep learning, as you can imagine, and most of them are kind of which features contribute most to the outcome. So beyond that, there's something called contrastive explanations, which is what would the outcome be if the features were different. So in maybe point one, we're saying, maybe what if we changed this nitrogen to an oxygen? Sorry, that's point two. Sorry, point one would be what percentage should each atom contribute to the outcome? Or maybe if you are using an AI for something predicting if there's a cat in the picture, a feature explanation would say which pixels contributed to the cat. Then a contrastive would be what would be the outcome. What would be the outcome if we change the features? So now we're not just looking at the features, now we're looking at the outcome changing. So maybe you say, what if I changed each pixel? Would we still get a cat out? And then a counterfactual is what is the smallest number of changes we can make to the features to get a different outcome? So that is if I have a molecule, what atoms do I need to change, or what bonds do I need to change to get something with a different outcome? And here's an example here. So my grant proposal was rejected from NSF. If I correctly formatted my references, it would have been funded. So this is something which is close. All I did was change my references, but the outcome changed. So you can sort of see how this is an explanation, right? So the explanation that you might say is that your references were not formatted correctly. That's why your proposal wasn't funded. But it turns out that that causality chain is very difficult to construct in that forward direction by saying it was the references that were the problem. However, the counterfactual is a little bit more direct. We basically find a situation where everything is almost the same, but the outcome changes. So here's an example in chemistry. So on the left, I have a molecule which will not cross the blood-brain barrier. And on the right, I have a molecule which will cross the blood-brain barrier. And you can see the small change that was made. So then the question is this an explanation for why the original molecule wouldn't cross the blood-brain barrier? And the answer is yes. The explanation is quite clear, is that you have this carboxylate, and that if you change it to an ester, you'll cross the blood-brain barrier. So I'm going to talk about some examples like blood-brain barrier, or I think inhibiting HIV replication. And these examples, remember that we're not actually talking about molecules that will inhibit HIV or things that will cross the blood-brain barrier. We're trying to explain a model which predicts it. So when I say that this is the explanation for why this molecule won't cross the blood-brain barrier, I don't mean we actually tested this on the blood-brain barrier. I mean, I'm trying to explain a deep learning model which does predict if things will cross the blood-brain barrier. The model is quite accurate. It has a 97% accuracy, so we can assume that these conclusions will hold up in a real system. But here, we're not trying to explain blood-brain barrier crossing. We're trying to explain our deep learning model, which can predict blood-brain barrier crossing. Whew, that's a lot. I'm not going to talk about this, but the real innovation of this paper was how do you find the counterfactual? And sort of, I'm not going to get to the math here, but basically what we do is we basically use an existing method that generates all kinds of different related structures. So starting from the top left, it shows you a whole bunch of similar structures in chemical space. So here's how our method kind of works, is that you start with a molecule, then it explores chemical space using this method. And then each dot in part 2 is a molecule. And then in part 3, we basically find the color is the outcome. So purple means it crossed the blood-brain barrier, yellow means it didn't cross the blood-brain barrier. Then in part 3, we identify the closest one with a different outcome, so the closest yellow dot. And then we do a little bit of chemistry magic and subtract the structures and highlight what was the change. So that's what the little red dot means, is that we deleted that alcohol group, or the carboxylate acid group. So this is sort of how this method will work. So here's a base molecule. This one is predicted to inhibit HIV. And then I show you 3 other ones that have different outcomes. And so what's really exciting about this paper, the reason why this paper is so important, I think, is that this method is the first which is agnostic to the deep learning model. That is, this works on any model regardless of how it works. And it works on things that aren't even deep learning. It works on things that are machine learning. It works anywhere. And I think that's an exciting outcome, because most of the existing methods required you to train the method on your data set, or they required you to work on a specific deep learning architecture. And then so now we have it down to this, is that you can install this package, and it's literally 3 lines of code. I mean, one of the lines is plotting, like it's 2 lines of code, and you can explain any deep learning model that takes as an input a chemical structure. So I think this is an exciting paper for us, and I think it's going to go a long ways in basically making deep learning more interpretable. Okay, so there you go. That was my science for tonight. If there's still appetite, I have a couple small projects that didn't work out as exciting as the first ones I talked about, but I'm happy to take any questions about the science now.
Yeah, please. Yeah, I think right now there's a collective jaw dropping that's happening. This is absolutely fascinating. Good. Yeah, no, in the best possible way. So we got a question for you here. Is chemical space here good coverage of the full universe of chemicals, or does it rely on actual instances that are vectorized?
Yeah, so the way this works, so like in this picture here, what we do is we use a measure called Tanimoto Similarity. And Tanimoto Similarity is an approximation of how close 2 molecules are. I say it's an approximation because nobody knows what the hell closeness means in chemical space, or like there's still debate on what that means. But so what our method does is it enumerates chemical space within a Tanimoto distance of about 0.2. So we're not trying to cover all of chemical space, right? That's some ungodly number of structures. We're basically enumerating all the chemical structures which are close according to the Tanimoto similarity. So on this plot, this is a PCA. So obviously a molecular structure is not a two-dimensional coordinate. So what we did is we did a PCA. And so on the left, we're showing our starting point. And the reason why it's on the left is because everything has a positive distance from it because we're using this similarity measure. And if you look on the right, there's this sort of tail. That's these things where you're getting into a funnel of things which are far away. So all of chemical space, the billions and billions of molecules that are far away from this molecule all fit into that little right tail. And we try not to explore that because it's a waste of time, because none of those things are going to be counterfactuals, because they won't be a small change, they'll be big changes.
Okay. Can you talk a little bit more about, again, this because I'm not overly familiar with deep learning. So you said so the point of this paper was to all right. I'm trying to think of the right way to ask this. So
no, it's fine. It's fine.
So you have the base molecule here is an actual molecule, right? That treats HIV or stops.
It inhibits HIV. It
inhibits HIV. Are the other three counterfactuals actual molecules that have been tested, or is it okay? So this is saying. So I guess how do you know that what makes the model say that these won't inhibit HIV?
Great. So good question. So the point of this paper is that we want to interpret a prediction. So our model predicted that the base molecule will inhibit HIV. Okay. And we want to understand why it predicts that it should inhibit HIV. Okay. And because these models are not inherently interpretable, we use counterfactuals. And so what I'm showing you here is that these three changes to the molecule will make it lose activity. So, for example, the bottom one is if you put a fluorine there instead of a methyl group, then you'll lose activity. So this might be an important binding site, right? On the other side of the molecule, you can see most of these changes are sort of about the solubility. You might argue, of course, it's not obvious, but there are things which are basically modifying, I would say, the number of hydrophilic groups. Yeah. So this just sort of gives you reasoning. So I think maybe this other example we had up here, this is another one where we're trying to explain why our model thought this would not cross the blood-brain barrier. And so you can see that this small change here makes it cross the blood-brain barrier, so we can infer that our model basically is predicting it's not going to cross it because of this carboxylate.
Okay. So the prediction is the prediction based on known information?
Great. Yeah. So that's the thing. So this paper is like, if you have a deep learning model, this paper allows you to understand it. Okay. And to interpret it. So in this paper, just because we had to, we made 3 deep learning models. One model predicts solubility, one model predicts if it inhibits HIV replication, and one model predicts if it crosses the blood-brain barrier. We're not the only people to do that. Many people have built models for that. But the point of this paper, I think what makes this paper exciting is that it doesn't matter what model you're looking at, this will work to explain your deep learning model.
Okay. I think I'm getting it. I'm starting to understand it better now. Okay, that's really cool. So it basically helps you pinpoint the things that you need to pay attention to from the output of your deep learning model.
Yeah, and I guess it gets back to the point I made at the beginning, is that you can make a deep learning model that perfectly captures crossing the blood-brain barrier, but it's not going to give you any insight into why things cross the blood-brain barrier. Right. However, with this method, it will allow you to start asking more scientific questions, like, why does this molecule cross the blood-brain barrier? And now you can start thinking about things like, oh, it's the ester, oh, it's the shape, or it's the molecular weight. This is a way that allows you to, I think, start getting some interpretation and maybe a little bit of science after you've constructed a deep learning model.
Yeah, absolutely. Okay, that makes a lot of sense. So I got a couple of questions as well. One person's asking about applying this to screening compounds. Basically, you could use this to start trying to screen things that maybe like you said, either have a group or don't have a group or something like that. So you start to pinpoint the major parts of a molecule that are of interest, or maybe have the biggest effect or something like that.
Yeah, so this is a local method. So I think this is a method that maybe wouldn't work to just like design a molecule, but like let's say that you have a drug that works really well, but it doesn't cross the blood-brain barrier.
Mm-hmm.
This method could help you modify your molecule so it could cross the blood-brain barrier. Like that's definitely possible. Like I said, we set out for this project, or we were excited about this project because we could explain any deep learning model. But every time I present this work, everyone's like, well, then could you actually tell me how to make my molecule cross the blood-brain barrier? And it turns out, yes, we can actually do that, but that wasn't the point.
Right,
but that's fine.
Right.
But I'm excited to help.
No, it's just really cool. The other question we got here is, when can you make the leap from explaining the model to then having confidence that you were explaining sort of the real world?
Yes. So you'll have to ask my colleagues in causality research. Yes, how do we make the leap to know we're explaining the real world? That's a very deep philosophical question because, yeah. I might have a deep learning model that predicts with 99.9% accuracy. But how it arrives at that accuracy may not be because it understands the mechanism or the physics of the problem. It might be because of something silly, right? Or it might be because of some correlation that I don't recognize. So yeah, there are definitely sort of, I would say, like adversarial ideas that you can have, or you can concoct sort of situations where the deep learning model learned the wrong thing, and then when you go to interpret it, your interpretation will be off. That's possible. But I would say that what this method does is it allows you to at least start understanding why the model thinks a certain way, so that you can capture these sort of pathological cases where the model learned the wrong thing. So I think that this is a step towards it, but I don't think we'll get to the point where a deep learning model is equal to a complete mechanistic explanation. Like I don't think if you can capture it with a deep learning model that you cannot then interrogate the deep learning model enough to figure out the mechanism. I think there still has to be some accompanying, other work to get at a mechanism. But yeah, I mean that's people are working on this. Like this is a whole big field of causality. Is like, can you construct a deep learning model, or an AI, I guess I should say, that can propose experiments that would capture that mechanism? So people are working on that at a deeper level, but I think right now that's not possible.
That makes a lot of sense. Okay. I think that's all the questions we've got on this part. So let's hear about some of the stuff that didn't work.
Yeah. So I mean, I should say like failed projects. So these are things which maybe didn't fail, but maybe were not as exciting or interesting. So this one, ClipMol, I worked on ClipMol for, I don't even know, like this is something I've been thinking about for probably a year. This is probably the most I worked on something. And it was, can I make an algorithm that will construct molecules that when you draw them, they look like a sentence? Okay, so like this sentence was bird. That is, can I make a molecule that looks like a bird? Okay, so this is an algorithm where you put in the word bird and it finds a molecule that looks like a bird. Like, I thought this was the coolest idea I've ever had. The dumbest, but the coolest, okay? And this one was a cat. Like I said, I want to make a cat, and this is the molecule it drew. Like, to me, this looks like a cat. It even got the butthole right. And I don't even know, like, this is like that little red dot. I didn't add that. That's like when you have a crossing on the plane of bonds. So I made this thing, okay? And it took an enormous amount of work, but you put in whatever you want. You put in a symmetric fir tree, okay? And it will make a symmetric fir tree. I think I have the animation for this, okay? So like you can watch the algorithm work, is that it slowly constructs a symmetric fir tree over time. Here, the score is like how much it thinks it looks like a fir tree. Look at that, okay? I thought this was so cool. Nobody thought it was cool. Everyone was confused. Nobody thought it was interesting. It doesn't work very well either. Like, I've been trying to get this cat back. I can never get the cat to look as good as it did this one time. But anyway, so this is ClipMol. I thought this was exciting. Most people disagreed. But anyway, it's out there. It doesn't work very well. And I think it's kind of a failed idea, but I'm probably going to keep tweaking it. So another idea I had was I wanted to take a molecular dynamics engine and hook it up to to an image recognition neural network. So that is, I have this particle trajectory where the particles follow like Newton's laws of motion, but the force field, the potential energy they feel, is coming from a neural network that can recognize shapes. And what I did is I told it to maximize the signal for a vase. So I put a bunch of particles in the center. I give them all velocities, and then they feel a force which is supposed to make them turn into a vase. And I look at this thing all the time, not all the time, but I look at this thing occasionally and I think to myself that I see a vase, and sometimes I don't think I see a vase, and I'm not really sure. I think it would be cool someday to get this to work correctly where like the particles actually make the shape that you're thinking of. But it turns out that just having particles move in the force field from a neural network, according to like a particular concept, like a vase or a cat or a dog or something, it doesn't work out. But I don't know. Every now and again, I look at this thing and I swear to God, I see a vase in the center, but I'm not sure. All right, last project that I would say, maybe I shouldn't say failed, but didn't really catch on. So this one is a programming tool. So you put in like an English sentence, like get the largest 5 folders in home, and then it gives you a command, that will do it. So then it says, get the current month, and it tells you what command to use to get the current month. So that's kind of been done. That's this Codex model from OpenAI. But then what we did is we modified a little bit, not modified it, but we come up with some special things to tell it to make it work with molecular dynamics and computation chemistry. So here I'm telling it to select the hydrophobic residues on a protein, and it constructs Python code to select the hydrophobic residues on a protein. What's mind-blowing to me is that it knows what a hydrophobic residue is. I mean, it is quite a surprising discovery. So here's one. It says, compute the dissociation curve of H2. So this is like, I would say in a very advanced computational chemistry problem, this might be like one of the final homeworks. So it knows how to build an H2 molecule. It knows how to construct, the calculation and how to do the separation. Then it asks us to use a more accurate method, so it switches its basis set to be a function call, so you can pass it whatever you want. And then it also does things that are like maybe trivial. So here's the text that says, show how to add a legend to the outside of a plot. I don't know if you've ever tried adding a legend to the outside of a plot matplotlib, but it's actually kind of confusing. And you just ask it to do it, and it'll give you a code example for that. And if you try to search this on Stack Overflow, you do not get a nice code example for this. Anyway, so this is something we made. I thought it was cool. Not many people use it. None of my students use it, even though we made like a Slack bot where you can ask the Slack bot to write code for you. And I think no one's used it in about 4 months. So there you go. So these are some projects that I think are cool. I'm going to stick by these projects, but they didn't catch on or they didn't quite work right. So these are sort of, I don't know, quasi-failure projects.
I personally think they're all really cool.
Oh, okay, good. Yeah, thank you.
And I do kind of see the vase, so you're not alone on that one.
I'm just late at night.
Yeah, exactly.
You can see
the
vase.
True. Yeah. The later it gets, the clearer the vase is. It's a good test. Yeah. No, this NLCC is fascinating. I've not ever seen something like it before, honestly. So
yeah, if you want to, we wrote a paper about it. This one actually turned into a paper. I think it's nice. Where did I write that paper? God, I don't know. Too many papers. Here it is. Here's the tweet about it. We show some other examples. So like here's the complete example for the dissociation energy of H2. This is the plot it makes, which is kind of incredible. Another one that's kind of cool is we ask it to like draw caffeine, and it knows how to draw caffeine, but it also knows the molecular structure of caffeine. Like it knows the smiles for caffeine. That was pretty incredible.
That is very incredible. Wow.
Anyway, so yeah, we wrote a paper about it. You can read the paper about like how it works and a little bit of the history. Yeah,
that's wild.
So that's all I got. Like I said, a lot of these projects are here. One of them that's kind of fun is I made like a fake AI startup that's run by dogs.
That's fantastic.
That advertises like these different things in a pipeline, like Emoji Math to Molecular Dream. Anyway, I have too much free time on my hands.
I would invest. So good, solid. I actually got one more question here for you, or
sure.
at least one more question. So this is actually from a friend of mine who's a chemistry professor, and he's wondering, what advice would you give to beginners to basically get started in machine learning and deep learning in chemistry?
That's a great question. So I wrote a book on it. I'll just go to the book here. It's dmol.pub, and read the book.
Solid advice.
I mean, I guess I should say, I'm not trying to be like vain here or anything, but like I wrote this book because there was no book on deep learning for molecules and materials. And it's an open source book, like people contribute to it. I think it's a good community resource. If you want to if you want more resources, there's a chapter here called Introduction to Machine Learning. And in that chapter, I have, 5 good starting points that you could also read that are competitors, not competitors, but like other resources you could look at. And then the Introduction to Deep Learning. So slightly different than machine learning. And then Introduction to Deep Learning, I have links to video series, online books, papers that are also good resources. I would say, I think if you're a chemist looking to get into these topics, then this is a great book. If you're a computer scientist looking to learn chemistry, then this is not a great book. So I think it's meant for people from chemistry or chemical engineering and materials who want to learn about deep learning.
That's perfect. That's fantastic. It's really great that you did this resource.
Yeah, thank you.
Yeah. Next stop, eChem. There you go. Yeah. So I think, I guess I'll give a few seconds here, see if anybody else has any final questions. But I'll go ahead and say thank you for a fascinating talk and a wonderful presentation. You're a great presenter. You give a great talk.
Thank you. Thank you.
To see. This was a really great explanation of what deep learning is and also what can be done with it. It's an incredible breadth of things that you've done. It's fascinating.
Yeah.
I thoroughly enjoyed the talk, so thank you for that.
Excellent. Thanks for having me. It was great to be in a venue where I could just, talk about whatever. And you said no time limit, so I really talked for a long time.
No, you're good. You're good. Like I said, this is what it should be. Like it's really cool. Like there's you had the true science in there, I guess, but all the other things were great as explanations of like what it can do, right? So like even though not technically research or whatever, it added to the interesting work that you're doing. So
cool.
It was fantastic. It's exactly what I was hoping it would be, and just it was wonderful. If I could get you to hang around for just a minute, we'll talk very briefly. If there's anything else that you'd like to say before we sign off, please feel free to do so.
Thanks for listening, everyone. If you want to connect with me, I post all this stuff on Twitter. Otherwise, I answer all my emails too.
Fantastic.
Thank you.
And I guess I'll talk with you very briefly. So I'll try and give links and things like that for anybody that's interested when I post on Twitter after this. So thank you to everybody for coming out. Thank you for all the people that followed. I've had a bunch of new people show up today. Please feel free to come back. We're here pretty much every Friday. I'll post a link to the Discord one more time for anybody that wants to join. Like I said, it's equally low key, but it's a good place. If you're working in science, come hang out. You can talk about what you're working on, talk about issues you're having, and people are very friendly and will help you out as best they can. So yeah, thanks again to Dr. White. Like I said, fantastic talk. There's really not much else to say. It was great. Thank you to everybody for coming out, and we will see you next week. Have a great weekend. Get boosted if you haven't yet, and we'll see you next week. Bye, everybody.